so tell me this. Matter of fact, don't give me the. Okay. So they give me this right here. And the function is what now? T cubed, read that to me. All right. So they give me this right here. Now, it's possible that they may have just given me the velocity function instead. So let's say it was 3t squared minus 12t plus 9. That would be the velocity. So let's imagine, we'll go through all the different scenarios here. So they may have done this. Now, for you guys that have some work down on this problem, do you have an integral there anywhere in your work? I would guess you don't, because when we did this was before we had learned about integrals, right? Okay, so this is how we would attack this problem before we had learned about integrals. Okay, so total distance traveled by this particle. Now, what we're concerned about, and it says from 0 to 5, and if I remember right, seems like somebody mentioned that we could plug in a 0 and we could plug in a 5 into the position function. Now, would that make sense? Find out where it started, find out where it ended, right? So it would make sense that somebody might think, oh, okay, well, let's plug in a 0. So boom, 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 we get 11. And plug in a 5. Do that for me real quick. Let's
31.
31. And again, this might be a no calculator, right? 5 cubed is 125. And 25 times 6 is what? 150. So that's doable. That's negative 25 plus 45. That'd be 20 plus 11. 31, is that what you said? Okay, so that could have been no calculator, right? We could have done that. So it's tempting to say 20 for the answer here, right? But it's not. Well, it might not be, right? That means it started at 11 and went to 31. But we don't know. It might have done this thing, bounce back and forth. So what's the only way to tell? Well, what's one way to tell if it bounced back and forth? And you guys can probably look at your work and see what we did there. What did we do? Well, yeah, that's kind of a guess and check way. I mean, we could plug in a 1 and a 2 and a 3 and a 4, right? And see where it was at those points. But other ideas. We'll get back to that thought instead. Look at your work. Maybe we didn't do this one together, so maybe you don't trust your work. I don't know. Factored what? Why would we factor that?
Couldn't you take the absolute value of it?
Well, okay, but remember we hadn't learned that yet, right? So I'm kind of wanting to go back to what we did before we talked about the integral. So Logan, yeah, I think Logan's right. We factor. Why? What do you mean solve? See, I don't have an equation here yet, so that's why I'm confused on why we're factoring. All I have is this. What? Why would we factor that? Well, okay, yeah, we got to be careful because this problem is actually a particle moving on the x-axis, so it's a little confusing to say x-axis. I think you mean t-axis, but you're okay. Which is what? When a function crosses the, yeah, we want to know where.
It equals 0.
What equals 0?
T equals 0.
No.
I don't know that.
The velocity. We want to know what t value. Why would we want to know when the velocity is 0?
Because that's what changes.
So. Okay, so Logan, back to yours. I mean, the reason we would factor is because we're trying to solve that problem, right? But that's what I was looking for. But then now, why? Again, say it again. Why would we care in this problem when the velocity is 0? Because that's how we will tell if it's doing this, right? The only way back then, before we had integrals, the only way to tell where this thing changes direction is it's got to stop, right? If it's going to go to the right and then go back to the left, it's got to stop, right? That was one of the main things we discussed way back in derivatives. That's the reason we do the derivative equals 0, because that was these peaks, right? That was at local max and min. In this case, it would be that point and that point, right? So if we want to find the total distance traveled, we got to find out when it turns around, if it ever turns around. Does it ever stop, right? So we're going to set that equal to 0. Now I can divide everything by 3 to make this easier if this was no calculator problem. And I would get this. And then you said we factored that, Logan? And what do we have? T minus 3, T minus 1. So that would be 1 and 3. And those are both in between 0 and 5. Okay, so that tells us when it turned around. So what might we do then? Plug them in where? Because we're doing this a lot. Remember, we've talked about this, but we're saying it. Remember, we used to have back in F prime, and it is 0. What are we talking about? Plug those t values back into what again? The position function. Because now that we know when they turned around, what do we want to know now? Where were they? Where were they when they turned around? Where was it over here? And where was it over here? We got to plug those back into the original. So now we would do x of 1, and that is 1 minus 6 is negative 5, plus 9 is 4, plus 11 is 15, and x of 3 is 11. So we've got a decent picture now of what's going on. It started at 11. It went where? To 15. Then back to 11. And then to 31. That's what this particle did. So how far did it travel? It went 4, and then 4 is 8, and then 20. It went 28. It went 28 units is the total distance traveled. That is a perfectly valid way of doing that problem. Okay? Now, isn't that kind of a list of candidates right there? I mean, think about it. Now, we were doing it in a context here, but, if we had this function and we were saying, it wouldn't be that same answer, but we were saying find the local max or the absolute max and min. If we were saying find the absolute max and min, well, right, absolute max and min, we do a list of candidates. What are the candidates? Where do we look? Endpoints. And where do we plug them in a list of candidates? We plug them back into the original, right? The original. So, plugged our endpoints into the original, didn't we? Where else do we look besides endpoints? Where what? 0? Where the derivative is 0, right? They might not be local extremes. They could be flat spots, right? But where the derivative is 0, okay? So look what we did. We did the derivative, set equal to 0. So those are candidates. We plug those back into the original, right? So in this case, a max min. What's a max mean in this particle problem? What's the 31 mean? That's the max. It's not necessarily finishing. It just happens to be finishing because it was at the endpoint. What's the max mean in this problem? What's a max mean in this problem? The farthest.
The particle has traveled.
No, not the farthest it's traveled. The farthest it ever goes to the right? But the farthest it ever goes to the right. And what's the minimum? Yeah, the farthest left it ever is. The minimum's 11, the max would be 31. If this was just a global max-min problem, right, we would have done the same thing, the same stuff. So you look at those steps, it's just like we would do with a global max-min list of candidates problem, okay? But it was total distance traveled. We had the particle going back and forth. And so what we care about is, does it turn around? And because you might be asking in that context, you might be asking in such a way, this would be a way to do this, especially if it's a no calculator problem. So let's imagine this. Let's do this in red. Now let's say we have learned about integrals, okay, as some of you were mentioning. So you hopefully, to be honest, because integrals are easier. So I would prefer, but I sure want you to understand both. That's my hope here, okay? So now we get to the final, you get a problem, it talks about total distance traveled. I hope this is what comes to mind. I hope this right here is what comes to mind. So we could set up an integral right here, which would be the absolute value of what? T of, no.
Oh,
No.
Speed.
Absolute value of velocity, right? Absolute value of velocity is total distance traveled. So what do we want to put in here?
3t squared minus 12t plus 9.
Right? From? Now, if this is a calculator problem, then this is a no-brainer. This is the way to do it. Right? Now you just type it in, and you got it. Okay? Wouldn't hurt to do that here real quick. Type it in. Absolute value. Remember, you don't get to use the vertical bar now. You got to go find, you got to go into your, I can't get it right now, but you got to go into your, where's it at? Down by the pi or the? By the 9, next to the 9. You got to go next to the 9 in there, where we get the derivative and all that stuff, and the absolute value bars are in there. Okay? Can't do that vertical bar that we do when we're doing a solve kind of thing. So you better get 28, right? Now, what if this is a no calculator problem? The blue? Because can you do that integral without a calculator? Not without doing a little bit of work, right? Because we can't just pretend the absolute value is not there and do an integral. Because think about it. Remember what we said? What's an absolute value do? This is like doing area, right? Well, the only way to do an absolute value area is to take all the negative parts and flip them up to positive. Well, what's the only way to find what the negative parts are if it's no calculator? What can you do to find out where this negative part is? Find where it crosses the x-axis. So you're going to have to still set this equal to 0, right? Which is at 1 and 3. And then you could say, okay, I'll do the integral from 0 to 1. And then I could do the integral from 1 to 3. And then I'll do the integral from 3 to 5. Now remember, this is all no calculator now. And tell me what that'll give me. Because now that I've taken the bars off, what is that equation inside them? It's velocity, right? What's the integral of velocity? The net distance traveled. So now what I would be finding, now that we've already put these numbers up here in blue, we already know. So from 0 to 1, I'm going to get what? On this one. If I work it out, which I'll do here in a second, what should I get on the integral from 0 to 1? 4 or negative 4? It went from 11 to 15. I'm going to get positive 4, aren't I? From 1 to 3, what am I going to get? It went from 15 back. I'm going to get negative 4. So if I was doing this problem, what would I do with that negative 4? I'd just make it positive. I'd say, oh, okay, I went 4 from 0 to 1, and then it turned around. See, and because here's the thing. By setting that velocity equal to 0, I'm finding when it's turning around. So now I can do the areas, because now I know in between those it's not going to turn around, because I found when it turned around. It's 1 and 3. So between 0 and 1, it's not going to turn around. It's going to go from 11 to 15. Boom, that's 4. Then it's going to go from 15 to 11. So that's negative 4. Okay, so now it's went 8. Okay, and then I'm going to go 3 to 5. What are you going to get there? 20, right? Positive. So that's how you would, so if it's no calculator, you've really got to understand what's going on. Yeah, if it's calculator, great. Understand this, know this is a great way to do it. But you got to know more, right? You got to know what's going on. I don't want you just memorizing a bunch of little formulas. I want you to know what's happening. Okay, so if this was no calculator, you would have to do this. You'd have to say, okay, let's raise that up to 3, divide by 3, that's t cubed. Let's raise that up to 2, divide by 2 is 6t squared. Antiderivative, that's 9t. Right bracket, 0 to 1. So we put in a 1. 1 minus 6 is negative 5. Negative 5 plus 9 is 4. There we go. and then minus 0, I put a 0 in, that's going to be that. Okay, 3 to 1, so I put that in there. Again, I'm going to get negative 4 when we do it. Okay, there really is not a, when you're doing a no calculator situation and you got the bars, there is no rule for what to do with bars. You just got to know it makes all the negative positive, and the only way to know what's negative and what's positive is find where this crosses the x-axis. So you end up having to set the velocity equal to 0 a lot, even in those situations. Okay, now I don't know, you guys may have, in the rest of this packet, just typed in your calculator. I'm okay with that, because most of the time that's okay. But you are going to run into it when it's a no calculator, and you need to understand this. Okay, so very important scenario. Okay, let's go to the later parts of the packet now, and that we hadn't been doing, and do you have any questions about any of those? We had some where we had tables, okay, but the idea was supposed to be working with integrals. They had some where you had to set up some trapezoids and rectangles. That's a good practice. Yes? Okay. Oh, okay, good. So, what did they, I assume they gave you a velocity situation? They gave you a graph. So it refers to this graph is what you're saying. Okay? So this is the graph. Okay. So, again, this all fits in with this. So, if we're going to do position, velocity, acceleration, right? That's what we got here. X prime, X double prime, right? Find if the initial position of the particle is this, then what is x11 is what they're asking, right? Now again, it comes back to this. It comes back to this. The integral of velocity from 0 to 11 should equal x11 minus x0. Is that not true? Isn't that a true statement? The integral of velocity, which is this, that's x prime, right? The integral of x prime should be x11 minus x0. So when I see that I have an initial condition and I want to find this other point, again, integral is a good way to do it. Now, yeah, we talked about Euler's method. We've talked about doing an antiderivative, but you can't do it. Macy, you can't do an antiderivative here, right? If they'd have given you a V equation, right? This is the next 3 weeks or whatever we have till we start our final. One of the things that we want to keep introducing, and even as we go through our files as we lead to the AP test, is bringing it all together and looking at the different ways we can attack these problems and picking the one that's the most useful to us. If they would have given me some simple la-di-da equation for velocity, right? Then what would you have done to find, and they told you x of 0 is 2, so this would be like giving you x prime. And they told you x of 0 is 2 and wanted you to find x of 11. What would you have done? Would you have just done antiderivative? You'd have just said, okay, x is equal to t squared minus 3t plus c. You'd have plugged in your initial condition over here to find out the c, right? And then you'd have plugged in your 11. And then you'd have had it, right? I agree. That's how we would have done it. And when you have equation, you do it. But they gave you a graph. So you don't have an equation. So you can't do an antiderivative, right? So you got to have another plan of attack. Okay? So that's what we're going to do here. So, x11, we don't know. This we know is 2. Can we figure out that? Can we go back to that graph and do that area? Sure, because it's just a bunch of geometric shapes. Okay? So we can go back here and we can say, okay, the area is, well, this is a 2 radius circle. That'd be 4 pi, but it's half of it, so that's 2 pi, right? And then this is a 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6 triangle. 6 times 6 is 36. Half of that's 18. So that'd be negative 18. This would be a 1 by 1, 2, 3. So that's what, 1.5? Did I do that right? Okay. So 2 pi minus 16.5 would be that area. Okay. So back to this page. So what did we have? We had the integral from 0 to 11 of v was x of 11 minus x of 0. So this was 2 pi minus 16.5 equals x of 11 minus, and what's x of 0? 2. So add 2 onto there. X of 11 would be 2 pi minus 14.5. Agree with that? There you go. Okay. Really trying to develop an understanding of all of these concepts as we go through. And if we do, we should be able to handle these different things. So that is a key. This fundamental theorem part 2. Sure, if fundamental theorem part 2 is normally used if I give you 3 to 4 x squared plus 7 dx, and you do the antiderivative, whatever. But I mean, that's the kind of fundamental basic way to use fundamental theorem part 2. But what we never want to forget is that fundamental theorem part 2 is this, right? Whatever that function is. And so if we can find this area some other way and have to find one of these missing pieces, that's a great way to set up a problem right here. If we have an x prime and we have one of the, starting point kind of thing, which means one of these, but we can find the other one. So it's another great way to use fundamental theorem part 2. Okay, anything else? Okay, how about these free response packets? Oops. Okay, anything in 2012? One, 2AC, 4D, 6B. Which one? 3B. On 2015? Were we supposed to do 3B? Okay, that was on the other one. Let me see if we can even do it. So no wonder you probably had a question. Oh, no, we should be able to do that. Matter of fact, we did that already, didn't we? Did you say D? You said B. Well, let's talk about it, because I think we already did this one. But that's good. That's one of the reasons I didn't assign it, because I was trying to stick with the area stuff. But this is one of those area function things. Now, we did it back before we knew about area function, but I told you it meant antiderivative, right? So what do we know when we see this right away? What should I write down? G prime is equal to F, right? G prime, when I see this, G is the antiderivative of F, so G prime is equal to F. So that tells me this graph here, F, is also the G prime graph. So when they ask me for G prime of -3, that's like asking for F of -3, right? So 1, 2, 3, and we go up here, and I'm assuming this, they say this is a line, so if I'm going over 2 and up 2, that means over 1, up 1, so that's got to be the point, -3, 2, right? So this would be 2. So G prime of -3 would be 2, right? So what's G double prime of -3? That's F prime of -3, which would be the slope right here, which would be 1, right? But again, it's important that you have this, because if they're asking about G and you're reading off of F, right, that's not good enough to just put those as answers. You've got to make a connection that, okay, when you're asking me for G double prime of -3, I'm telling you that's the same as F prime. So it wouldn't actually hurt in your answer. If I was doing this one, I might even do that. You know, G double prime of -3 is equal to F prime of -3, which is equal to 1. All right, what else? Anything else? Either one, 2012, 2015. One D. Okay, so we got one of these situations with this, kind of like the sand problem. We got we got water going in, like running off your roof into a drain pipe, but then the pipe is blocked, so allowing the water to drain out the other end of the pipe at this rate. So in other words, it's not going out at the same rate it's going in, right? In other words, okay, which normally that would probably be the case. So the water is going out at a different rate than what it's coming in. All right, and so that's from 0 to 8. And there are 30 cubic feet of water in the pipe at the beginning. Like we talked about that sand problem, there was no sand in there at the beginning, but now there is. The pipe can hold 50 cubic feet of water before overflowing. For T greater than 8, water continues to flow in and out of the pipe at the given rates until it starts to overflow. Write but do not solve an equation involving one or more integrals that gives the time W when the pipe will begin to overflow. Okay? So what number do you know happens when it's going to start overflowing? When there's 50 cubic feet of water. Now these equations are cubic feet per hour, right? So how are you going to go from cubic feet per hour to cubic feet? With an integral. Again, antiderivative, but really it's an integral, right? It's an integral. So that means, so if I did the integral from 0 to 8, I don't know if you want to write this down yet, but of big R, tell me what that would give me. What would that, I mean, don't give me the actual number. Explain it to me. I don't like the word through there, but you're close. She said, how much water flowed through the pipe in 8 hours? Because to me, flowed through means that it went in and then it went out. And so that's not quite right. That's the total amount of water that flowed into the pipe. Now, whether it actually went out or not, I don't know. It may not. It may still be in the pipe. That's the total amount of water that flowed, would be flew, that'd be a little different, flowed into the pipe, or went into the pipe, okay? All right, now, what would the integral of, from 0 to 8, of D be? What would that give you? That give you cubic feet, right? But what would it be? Explain it. Amount of water, that's a total amount that went out, right? So what happens if you subtract those? Isn't that the amount that's in the pipe, right? This is all the water that went in, minus the water that went out, should be the water that's the new water that's come in that's still in the pipe. So do we just set that equal to 50? Well, first of all, we can't have 8s there, right? We're going to put, now why wouldn't I put T there? Because R and D are both in terms of T, right? So I want something else, so I'll put X. Okay? And then set that equal to 50? No. We're missing one piece of information. Right? This is going to be the total amount of new water that is still in the pipe. This is the amount of new water that went in. This is the amount of new water that came out. You subtract those, that'll be the amount of new water that came in, but there were 30 feet in there already, so we only have room for how much? 20, right? So you could have just set it equal to 20, right? You could have just set equal to 20 instead of setting it equal to 50. Okay? Right? But do not solve an equation. Now, this is a no calculator one, so that's why they said do not solve, because it would get into where you can't even do anything derivative of that and just be a mess. Okay? If this was a calculator one, they might have went ahead and said, go ahead and answer, but they know then you're just going to type in your calculator, right? So again, it's all it is units. All it is units, but it's more than just units. It's like over here. I mean, yeah, when we start this, integral of miles per hour is miles. Yeah, that's good to know. But what kind of miles? What are the miles, right? Is it net miles traveled? Is it total miles traveled? Is it amount? Is it cubic feet? Yeah, it's good to know that this integral is cubic feet. But what? It's the cubic feet of water that's flowed in. This is the cubic feet of water that's flowed out. So you got to know more than just that. Okay? All right. So back to A. Did we do A then on that one too? Yeah. So how many cubic feet of water flow into the pipe during the 8-hour time interval? So wouldn't that just be this integral? 0 to 8? It'd just be the R, right? It'd just be that one, 0 to 8. And then, were you supposed to actually do that? And is this a calculator one? Oh, never mind. Okay. Yeah. Good. Otherwise you wouldn't be able. So you can just type in the calculator. Here I think what they're saying is all the free response questions were 9 points. So I think what they're saying here, the reason they said do not solve is they're like, okay, we've already got all our 9 points. So we're not going to give you an extra point for solving it anyway. So forget it. And we know you're just going to type in the calculator once you got it anyway. So that's why they and they often do. Because if you got it set up, that's really the battle. And then, I wonder if you would lose that point. I forgot this right here. So where should the W be? Where should I have W in here? Yeah, I should have that. Would you miss that? Maybe. Like, for example, on this particular one, this might be worth 4 points. You might have 4 points for having the 30 on there, or a point for having the 30 for setting it equal to 50, or having a 20 involved somehow, for having the integral R minus the integral D. So you probably could have got most of the points, but you might have lost one if you didn't have a W there. Yeah, that should have been a W. And to be honest, it should have T dt. It should be D of T dt. And could you have made that just one integral and done R minus D? Yeah, you could just have one integral R minus D instead of 2 separate. Okay, that's why they said here one more. Okay, good question. Good question. What else? Anything else? Nothing. All right, let's hand in the sample 3. We missed today, Steph. All right, and then hand up the motion packet. Make sure your name's on them now.